Cool. So operator overloading, I was mentioning that this is one of my favorite lectures of the course. You know why? Because I think it's one of the easiest lectures. I gravitate towards stuff that I understand quite dramatically. And it's fun. I don't know why. That's just me sharing a little bit about myself. That doesn't really matter. What this lecture is about is it's really about defining our own types. When you think about object-oriented programming, I think a healthy way to think about it is like, it's really easy to work with an object, you know? Like, you don't need to know much about object-oriented programming to work with a string.length, right? You're working with an object. But when it comes to OO, most of the difficulty is around creating the object, as in defining it yourself. The person who writes the string library, the person who writes the vector library, that's where all the complexity is in this space. And when we define our own types, like if we were to make our own vector or make our own string or make our own anything really, we want to be able to use and define common operators as well. Common operators might be like plus, minus, divide, equal to, things like that, less than, greater than. They're the kind of common operators we want. You might be thinking, when will I define my own type? There's lots of different times that you might define your own type. Probably the first time I remember having to write my own C++ class was something to do with RoboCut, where we were basically, the way we were trying to detect a ball at the time, because they just recently moved from this orange ball you see here to this black and white ball. And for the people who were doing the computer vision work in C++, it was a real nightmare for them, because the orange ball was really easy. You know, you just kind of looked for parts of an image that had RGB values that like vaguely represented red, and then you were like, there's the ball. You could find it pretty easily. Whereas this stuff was really, really hard, because you think that's a ball and your brain's quite good, but the robot's quite dumb, right? So it's like you got white lines everywhere, white lines here. I mean, do you know what I mean? Like, how is that not a ball? It's jerseys or that fence and stuff. So they you know, the other couple of guys that were writing, you know, they do pretty smart things. Like they'd figure out where the horizon is. That was a really common one. You'd see the bottom of the field there, right? And then you'd be like, well, I'm not going to look at anything above that. But one of the next things they wanted to do was the way they approached it was like they had a quick scan through the image using a heuristic for anything that looked vaguely like it might be a ball. You know, basically anything that's square-ish that has some kind of patterns that might be interesting. And they would collect maybe 100 of them, and then for each of those 100 areas, we called them regions, it would run it through a what is it, like a binary tree, decision tree? Like an ML learned decision tree, I think it is. Basically like a computer generate a bunch of if-else statements based on, you know, some training. And one of the classes we wrote was the regions. So all these different regions on the robot, candidate regions, we had a class for it, because it wasn't just X and Y coordinates, there was also some metadata in it, like, you know, how many squares or how many circles or what's the average color, right? Nothing too complicated, just like standard class definitions. But that was in C++. And there's, if you build a big enough system, you're often going to find that there's going to be data types you're going to need to create. And I don't know what the postgrad equivalent is, but if you're an undergrad who's done 2511, you'd also know that, you know, creating your own data types kind of comes up. But in those courses, and again, maybe Python for the postgrads, if you've made your own classes, quite often they're going to be quite simple, which is just like they store data and they have some functions. And in a way, the basics of teaching classes is often reduced to just a convenient organization of associated data types and functions, right? Like, oh, I've got, you know, this region, and there's 3 or 4 functions I wrote for it, and there's a few data types I need to store for each region. It's like a nice little packaging of things, but we rarely talk about operators. So if we have a look at a piece of code like this, oh, I know it's small. Let me see if I can open it in the editor. This room and the lights, every week I come here, I'm always like, I hope they fix it. All this money on rooms. All right. So again, ignore a couple of things here. This code's been Clang formatted, so it's a little bit ugly. But I've got myself a class called point. It's a very straightforward class. It just stores an x and a y coordinate. You know, it's just like a Cartesian point. It's got 2 getters, int x get, y get. Cool, it's a constructor that uses the constructor initializer list to populate stuff. That's why the constructor body here doesn't need to do anything. And then we have our static point here. We have a static function. That means it obviously isn't associated with a particular object instantiation of the class, but just exists once off. And down here, I am creating a random function unrelated to the class called print. And what it does is it takes in an output stream, a reference to an output stream. An output stream is simply some kind of stream that you can stream information to. And it also takes in a point, a reference to a point const reference called p. And when I call print, all it does is it sends to the output stream x and y, nice little string brackets and comma between it. And I have my static add function where I pass in point 1 and point 2. And it adds those 2 points together and gives me a new point. And I'm reusing the constructor that I've got here to make my life a little bit easier, because I'm returning a whole new point that is just constructor initializer listed with those two things, and naturally x and x are going to be integers, so they add together. And then if I have my main function, I've got my 2 points, p1, p2, and then I go and print. I give it standard cout, because that's the output stream I'd like to send the stuff to. And then I give it point add, which is going to give me a new point, and that's going to get passed in by reference. And then I also just dump a new line at the end. Right, so fairly simple little program. Got to sneeze. Oh no. a little bit messy, but yeah, Tim on the chat says don't need to define add as static, just declare it. Let me get that up for you over there. Yes, just declare it that way. Don't need to define it as static, just declare it that way. I guess so. Basically, I think Tim's asking about, do we not need static there? Not 100% sure. I mean, let's go away and just try and compile the code just to warm ourselves up. What do we got? Make point 1. .1, point 1. Okay, our code runs and prints out 3 and 5. That's cute. That's cool. Now, if we move on slightly from that, this was our best attempt to put it together, to print that out. But in an ideal world, we would much prefer to have a semantic like this, right? This would be nice if you could just standard cout p1 plus p2. So you say p1 plus p2, they somehow add themselves together into a new point, and then that new point just gets streamed out to the standard cout. Now, obviously, this isn't going to work because the compiler right now has absolutely no idea how to do that. It doesn't know what plus means there. It doesn't know what sending that to standard out is. I know it's intuitive to you as a person, but if I was to simply say here standard cout p1 plus p2 and then put that there as well, I'm going to get an error. Invalid operands to binary expressions point and point. It doesn't understand what the plus is. So the reason I put this example right at the start of the lecture is because I think this best summarizes what the entire topic of operator overloading is about. It's going to be fairly similar in other languages, but tonight we're specifically looking at C++. And operator overloading is defining all the kinds of operators like this so that we can create our own types that behave how we expect them to be. So in this case, it's defining a plus for the point and a way to stream to standard cout. Because if we can define those two things, then the compiler will know what to do with it. So if we start firstly just by overloading the basics, these two here, and I'll pull them up again in the editor because the screen's a bit funny. Let's have a look at this. Ignore the word friend for now. We'll kind of unpack that in a sec. Just tighten this up. Sorry if my voice is a bit funny. I've been talking a lot of today, so. Cool. So what I've got here is I've gone and put two lines, two kind of prototype lines in my class, and then I've come and defined them further down. There are still some things about the friend that we'll unpack. But here's what you notice. I have defined an operator plus here that takes in a reference to a const point and then another reference to a const point. And then it simply returns that new point that we've expected, right? Easy. And then I've got another one here called operator less than, or operator output stream, that takes in an output stream and a point and does that exact thing that we had before, and it returns a reference to an output stream. You'll also see point is the return type for operator plus as well. And it's not a reference because we're creating a new thing inside the function. So I think one thing to demystify at the start here is that when it comes to these types of operator overloads, they are extremely prescriptive. And what I mean by that is that it always looks the same. So if you were making an operator overload for a string, it would look like string operator plus string const reference string const reference. Do you know what I mean? Like there's not a lot of wiggle room in these function titles and parameters for much variation. It's always the same thing, like give or take nearly every single time. And in some ways that makes it kind of hard because you have to kind of figure out what they are for each operator and Google it and stuff. But in some ways it makes it easy because it's you kind of know you've gotten it right or not. You know what I mean? There's not a whole bunch of instances where you're adding together non-const points or where operator plus is returning nothing. And you might be like, why is it this certain way? Or a good example is like here, operator less than. Sure, Hayden, but that's a function that's taking in 2 arguments, but I'm not doing that anywhere, so how does it know to call that? And if you want to think about it, what's actually going on is that when the compiler comes across and it sees this P1 plus P2 here, what I want you to imagine that it's doing is that it's literally seeing that plus, and it is then going to the type. Say it sees that left and right are the same type. It's going to that type, and it is going, hey, I'm just going to do this. Like that. So that's what the compiler is. Think of it, it's like that's what it's doing. It sees that plus and it converts it to that, so it knows what function to call. And then when you try and stream it out somewhere, it does the exact same thing and does this. And that's basically what ends up being done by the compiler, is it looks for those operators, like those particular function titles, operator something, in your class, and it calls those instead. And that's how you can kind of customize the behavior of a particular class you're writing. And it actually makes a lot of sense, right? Because operator plus, again, has to return a new point. It's not going to modify the things it takes in. That would be crazy here. Like if you just randomly had LHS.x++, that would be wild. Just like every time you call the plus operator with 2 things, it just mutates one of them randomly. That would be pretty weird. You'll also notice that the operator less than has a standard O-stream reference return. It's like, why is that? That's weird. I don't care about what that returns. I'm just trying to print something. But think about how standard cout works, is that when this here resolves this function, what do you want that to return to? You want it to be the standard cout itself, because a lot of these stream operators are like chained together. Does that make sense? Because you can kind of think about it like when you're down here and you write standard cout A, B, C, how this will actually get resolved by the compiler is the compiler will come along and say, oh, what's going on here? Well, that's actually just an operator plus of standard cout and A. Cool, because that's what it was doing. And then it will resolve that to standard cout because it's just printed it. And then it's like, oh, what's happening here? He's trying to print operator plus of standard cout to B. So you always need that standard cout to be returned there so that it can, basically like, it's not quite recursive, someone might call it that, but chaining them together is maybe the way to think about it. But for every different operator, there's a different way to define it, and it's pretty well described online as well. Yeah, question?
How is the order of operations decided? Is it just left to right?
Ooh.
Because it could be like less than, and then the combination of those.
That's an excellent question. So everything we're talking about is operators. Operators describe plus, minus, less than. And this lovely page on CPP reference does point it out, which is good. It's very detailed, but you can kind of see like it will always scope resolve things first, for instance. So like, and that makes sense. Like if you're like standard, A plus standard B, It's just saying that it's going to glue standard to A and standard to B before it does the plus. But then, you know, the dots and the A's kind of come first, and then, you know, pluses, negations, things like that. So when we look at the less than, that's going to be a lower precedent than the plus. So that's a good question, because, like, yeah, how does it know? It knows because a bunch of committee people, whoever they are, wrote this definition. Then people who maintain compilers go and implement the compiler according to these rules, and then we program according to, you know, both of those things. So.
That would be outside the scope, like when you're writing the you wouldn't be able to.
Correct, because the overloads are, the operator overloads are in a vacuum, right? Like, they don't know which order they're being called in. They're just trying to help understand the behavior of how your type does a particular thing. If that makes sense. You can do really weird things. Just to show you, like, if I have a point here, 1 and 2, and, you know, when we add them together, it's going to be 3 and 5, right? And we've seen that already. If I make point 2, yep. Really screwed that one up. Yep, and then I run 4.1, 0.2. 3 and 5. You can do all kinds of crazy things. Like, I could just add a +7 there and completely screw up how addition is defined. You know? Like, you're in control of all of it. You could change the standard C out here to be like, hello, here is my data. And it will just, again, behave like that. The reason this is also useful is because it helps you understand, you know, that when you standard C out a string on the terminal, it's not just the C++ compiler isn't like, oh, of course, an STL standard string. The C++ compiler has no idea what an std string is. It has to go and talk to the std string class definition, which has an overload for operator output stream in it, and it uses that. So all these behaviors are defined by the classes themselves. So got a good question in the chat. Tim says here, these are bit shifts in the table. Are I/O streams perverting those operators? I guess so. I remember reading that now. Now I'm kind of curious where the output element is. I don't know. Maybe they're not considered a base operator, and they'd come last or something. But yeah, it's true. I kind of mentioned that this was after addition and subtraction, but I guess that's a different thing. Then I'm like, I wonder how that even works with. Okay, I follow. All right, we'll come back to that. Okay, so using operator overloading allows us to use currently understood semantics. When you have 2 points and you add them together, people expect certain things to happen. When you add 2 strings together, this standard string, they defined it to add the 2 strings together and create a new string. You know, like, it's all defined somewhere by the people that write the types. C++, you can operator overload nearly everything. It's kind of hilarious, actually. Like, we all know a little bit about operator overloading from, like, Java's toString or Python's double underscore string. But I don't know where the list is. Where's that? Operators. There's a very long list somewhere. I'm not sure where they I don't remember where it is, but you can honestly, like, operator overload everything. You can operator overload dereferencing. You can operator overload all the bitwise stuff. Some of it makes sense. You can operator overload new and delete. Even I didn't know that one. I don't know in what world you'd be interested in doing that. Sub makes sense. Plus, minus, divide, modulo. Most of this, I'm like, I can't imagine why in a million years you'd want to operator overload it, but you can. It's extremely powerful. You can really define things as much as you want. One area you need to be careful with, though, because this does clean up code and understandability. It's like generally big pluses, right? People can add your 2 points together. If they want to see how 2 points are added together, they don't have to go looking for some random static point add function. They can just look for operator plus. Sad. But where you have to be careful with it is pretty much instances where it's not immediately obvious that that's how it works. So if you ask yourself, I'm going to overload an operator like plus or minus or something like that, and then you think, will 9 people out of 10 understand clearly what this means? Is it obvious? Is it commonsensical that it should behave this way under this operator? If the answer is no, it's better to define a different function for it. And by that I mean that, let's say this less than. Let's say you actually, for some reason, I don't know why you would, you actually want to print it out as like, you know, the sum or something. Let's say originally you were like, yeah, okay, p.x plus p.y. Now that would be silly. I don't know why you do that, but let's say you want to print it out that way. If you don't think it's immediately obvious what that is, then what you would do is you would literally just go and make a function like we saw in the first example. Go make a random function and you could call it like, you know, print sum or something if you want to. Let someone deal with it that way. Don't go and kind of confuse and things like that. Yeah, I keep running out of space. That's okay. Doesn't really matter. I don't really use the recordings much anyway. Cool. Okay, I had a big fat table in the slides that I had a brain blank and forgot about. That's probably what I was thinking of. I was like, where's that table? Somewhere on the internet? No, it's on the next page. So, broken it up here nice and easily for you. Like, and I've just unincluded all the boring ones, like I don't know why you'd ever want a bitwise or overload type, but you know, less than, sorry, in input output, I think that's meant to have 2 arrows. I think the slide software's getting rid of one of them. Basic arithmetic, relational inequality, they're pretty standard, right? Equals and stuff. Assignment, A equals B. Compound assignment, cool. Subscripts, yep. Increment, decrement, arrow dereference, call. Maybe not so much call. Now, one thing here, 2 questions then. First one is, what's the difference between a friend and a member non-const? And also, Sulux has asked the question, what does no discard mean? So no discard is, I think it's something that Clang format either used to or still does pick up on, but it should be a format error where if you call that function, but you don't actually assign it or do anything with it, you get a warning. So what I mean by that is you'll see down here, someone's using it, p1.x to kind of construct something. Sometimes a way people can write buggy code is they'll simply go like p1.x like this, and that'll be their line of code. Why would they write that? That seems really silly, but some people might think it does something, you know? Like, you know, you can call functions that actually print or they have a side effect and you're not really expecting to do anything with the return type. That's why they might do that. So no discard in this case, I'm pretty sure throws a Clang format error. And it's like, hey, you said that when someone calls this, they can't discard the result, but someone has done that down here. You've called the function, they've gotten a result, and then they've tried to just throw it away into the ether. That's not good. So that's what that is. Yeah, I think it was the same one in the previous lecture. But what I wanted to point out here are friends and members. I don't think we covered friends in the classes lecture from memory, right? No. I don't know how that's just vanished, because it used to be in the classes lecture. Doesn't really matter. A friend is a funny idea. If you understand member functions in C++, like x and y, you know that member functions are basically functions that you call on an object and they have access to that particular object's data. You know, like this one here, the x and the y. And then you have static stuff, and static stuff is associated with the class, but it can't access an object's data because it kind of operates above the object, you know? It's not associated to a specific object, so you can't do like p1 dot. There's basically no this in it. To say like standard C out this anything, that doesn't make sense. There's just no this when it comes to static stuff. Where a friend differs is a friend is basically a class that you define outside of the class itself, But when you mark it as a friend, it has the capacity to go inside the object and break the abstraction of the object. I don't like words to explaining things to explain things, but let's look in this case. This point here, operator plus and operator less than. In theory, nothing stops me from coming down here and defining these like this, just to be clear. They don't have to have anything to do with the class, right? In fact, I don't even need those lines. I could just create an operator plus called point, could take stuff in, see how it's using no this. But what I can't do is I can't do what I'm doing here. I have to get this through the public API, you might call it. Right? Because if anyone has a particular object like LHS or RHS, which is a point, you can call .x and .y the function on it, the method, right? Because it's a public part of the function. It's up here in the public part. But I can't call .x underscore because it's private. That's just standard class stuff, nothing super new. And same here. So those two things are totally fine. These are not the best examples to kind of demonstrate friends. What a friend, when you mark something as a friend, what I would do is I come up here, I grab the function prototype, and I come up and I basically paste it here with the word friend in front of it. And I'm essentially taking a function that has nothing to do with the class or the object. I'm saying it's a friend of that class, and that's kind of like half privileges. It gets a little bit of privileges in that class, and that privilege is that when I use a type of that class, I am able to access those objects' private members like this. So if I have this piece of code, which is what I had before, and we just try and compile that. Let's get a baseline again. Or is that not going to work on us? What's the problem? Expected semicolon. All right. No member named X. Oh, I haven't defined it. Nah, I was thinking of the other one. Let me just quickly get these in now. I'll make them small. Yeah, so that's assuming that there's an X and a Y. But, so that all works fine. But if I didn't have that, I'd be like, well, I can't obviously use that. So instead here, I need to just reference the private fields. That still works here, but if I was to get rid of these friends, it won't work. And here it says X underscore is a private member of point. Okay, so random function can't access private members of a random object. If I mark them as friends, they now can. This also makes sense because this is how you could have a function that might take in 3 different types, and you could mark it as a friend in each of those types so that you can access it. And it also makes sense because the declaration of it being a friend is done by the person who manages the type you're trying to access. So you can't just kind of randomly break abstractions by being like, I want to access the private members of this, because it's the person of the thing that puts it as a friend. Suluk says, are friend functions similar in usage to static functions in that they're not really fully related to a specific object of the class? I mean, they have that similarity, that like kind of vague similarity. I definitely kind of, I might talk about them as another kind of static, but they are a little bit different in that static stuff, actually static stuff can access, I think, private things from memory. Let me check. We can check. I don't know. I wonder if static can. I think it can. Let's try this one out. Can't remember off the top of my head. Seems to be fine. Print. Bottom of terminal's off screen. Damn it. I gotta make my dock bigger again. Hopefully that's okay. Let me know if it needs to go up more. But yeah, so remember that when something is static, it behaves also like a friend in that the static class of that type, like because I have a static member function or method called add, it can access private things of the points. But a friend is a bit more flexible. Like you got to think, a static is a special type of function for a class. A friend is more just like a random global function that has privileges in wherever you ask it to. So they do have some similarities, but they are also different as well. Cool. So some are friends, some are members. All the ones we've talked about are friends so far, so the member ones will make some more sense in a second. This overload input-output, we've kind of talked about it already. I don't really need to cover it too much more, but what you will see there is that this is an example of us having a friend for both the input stream and the output stream. So output stream, nothing new. Input stream could be completely the same. Input stream would be what you do when you say like, hey, standard C in to P. So if I wanted to, I could ask you to write me something where I could basically, on this line here, I could create a new point and I could say, now the terminal's going to prompt me for some stuff and you're going to type it in, and you need to write a function where that input stream will feed you things and you do something with that point. So maybe that's how you like construct a point on the terminal, you know, as you like enter a couple of numbers or something. Very random, that's why it's not there. Just because you can doesn't mean you should, right? With a lot of this stuff. Sometimes it's best left alone because it just doesn't make sense. But we've done a little bit with input-output. Now, so I'm just reading. Someone says, there are some examples he's shown in the lectures that haven't been in the slides, and I don't really want to go through all the lectures. There's one piece of code, which is this one that we updated today, but besides that, everything in the lectures is in the slides. They're not really the different. I just look at, I'm literally looking at what you guys are linked, so I'm not too sure what that's in reference to. So, compound assignment. When we look at a point here, we can operator overload not just the pluses and the minuses. Like we did an example with the plus before. We can also do the plus equals and the minus equals and the times equals and the divide equals and things like that. What's important though is this line here that says sometimes particular methods might not have any real meaning and they should be omitted. In this case, what does dividing mean? Makes sense. I know how to add two Euclidean Cartesian, what is it? Cartesian coordinates together? X and Y. Sure, I can subtract them too. What does multiplying them mean? Maybe depending on your use case, that might mean something. You know, multiplying two vectors, maybe it doesn't. Don't know. Dot product, whatever. Does divide equals mean anything? Maybe. Probably not. That would be weird. If I gave you two Cartesian points and was like, divide them, what would you do? You don't know. I probably don't know. So sometimes we don't need to overload everything. Each class can have any number of operator overloads for some things like operator plus. So if we come here and we have a look at our operator compound assignment, and what I've got here is just your standard like defining the function in the class and then, declaring it in the class and then defining it later on. What we have here is we don't need to define the divide, equal to, right? The plus equal to, we could go and define it here by simply saying, this is the definition. It's the same for every class. The point class has a operator plus equals. It takes in a reference to a const point, and it returns a reference to a point. Okay, so it takes in this other point, and all I do is add the x and y coordinates together. Wow, and then I return star this. That's not using raw pointers. That's just like this, I'm literally just returning the point that I am as the object. Really boring stuff. And again, the reason this topic's kind of quirky is because to implement that, it's really not, it's just not hard. Like if you were making a point, the hardest part's figuring out what syntax to write. Do you know what I mean? And that's why I was saying that in assignment 1, you nearly have to be a little bit thoughtful, thoughtful how things change, because assignment 1 is very much, here's an algorithm, it's slow, it's performant, we have to think about how fast it's going. You're probably having to remember some computer science theory you haven't thought about in a couple of years. Whereas this stuff gets more into like, it's not algorithmic, it's not unperformant, it's just like, can you get the syntax down and get it right? So I could go and define the other ones too if I wanted to. So what is minus equal going to be? Well, that's just going to be the same thing. So much the same thing that I will comfortably copy and paste this here. There you go. What is times equal going to be? Well, let's just pretend for a second that we're going to, make it really simple and just multiply the two things together. But then this one's really interesting. We've got another one here. This is another operator times equals, but instead of having a point there, we have an I. And this is here to demonstrate that when it comes to some operators like operators times equals, you don't actually need to have like always the same thing on the other side. You could do something else. In this case, it's like a scalar number coming in, So like, let's say you have a point 1, 2, and I want to, multiply that whole point by 3. So that's just like expanding the scale of the point. So if I was to, in this particular code example, I don't even know if I have it compiled. Let me check. I don't think so. I think this is the one I had problems with the lecture slides. But if I was like making this code, int main, you could go and make a point, right? Order p equals 0.23, and then you could come along and say, well, p times equals 3, and that would give you a new point that's like 6, 9, right? You could do that. Now, how does the compiler know? Well, it has a look at what are you actually, what have you got on both sides? So if I had these two lines here, p times equals p other, and p times equals 3, well, the compiler is going to look up which of these two particular operator times equals you have, depending on what types it sees on those arguments at the bottom. So, pretty cool. Who's bored? Who's having fun? You're very nice on that survey. I asked about on the. I was like, "How's the course going?" And everyone was all chirpy. Can't remember what you all said. 3%, 5 votes, 5 people are out. Good-ish. Look at that. Room for improvement. Try and make it more fun for you all. For the people who are average in math, I think particularly average, anyone in this camp as well, just email me if you have any random feelings about the course. Always happy to help. It's a fairly straightforward course, so I'm happy to chat about it. Straightforward in structure. Some of it can be hard, of course. Okay, relational and equality. These ones also somewhat manageable. Double equals, not equal to, less than, greater than, less than or equal to, greater than or equal to. Cool. It's not the hardest thing in the world. You just kind of have to look at it sometimes for a bit. You'll notice that with equals and not equals and stuff, they're all friends. I am defining these in line in this case. In assignment 2 and in the general, best practices guide, we do tell you to not define your functions in classes inside the class body, but to do it outside. It's only done here because the lecture slide gets really long otherwise. So normally you would go and actually define it underneath, like we did in the previous one here, where we did that. You'll also probably start to make more sense of things. Like, because these here in the previous example were member functions, they were actually functions of the class that we invoked by saying, this object, we're operating on it. They needed to be scoped with the point here because they are in that class, whereas these Boolean operators, they're not, which is why you'll see that you don't, because a really common mistake someone will make is they'll do this. They'll say point, colon, colon. Makes a lot of sense, It's like operator, output stream. Okay, it was part of the point, but it's not part of the point, and that's probably one of the biggest conceptual gaps to get, because you have member functions that are part of the point, like this one, and then you just have what I'm referring to as random global functions that just happen to, need a little bit of access to the underlying data there. You had a question. Oh, well, there you go. Good job. Good job. Were you one of the average? Did I just move you up? Oh, thank you. It's very kind. So these are all friends. And what I think is worth pointing out is this stuff here, because it really helps understand how operator overloading doesn't turn into an absolute, endless bumbling piece of chaos, which is once I've defined less than, I can go and define my greater than by simply checking if P2 is less than P1. If that makes sense. So I can leverage what I've already created. And then my less than or equal to, it's a little bit of a head mess here, but because, if P1 is less or equal to P2 is the same as not P2's less than P1. I'm not going to lie, I haven't seen the slide in a few years, well, besides before the lecture when I look at it. And I look at this, and even my brain straight away just kind of goes like, what? But I know you sit down, you reason with it for a moment, and it kind of makes sense. You can also express these things in other ways. Some people, for instance, might write this initially a bit uglier as like P1 is less than P2 or P1 equals P2. That's an okay starting point. Does the same thing. Clean it up later if you're feeling adventurous. And so same and so forth, right? It's all kind of along those lines. I don't need to run this code because I think it's fairly straightforward. Was there a question, or am I losing my mind? Yeah.
One more on the previous thing. One of them had the point, colon, and the other, this one. Why does that one have point, colon, the other one's saying?
They should all need it. Was that working? Oh, we never compiled this, so I think that's just wrong. Basically, but before today, someone pointed out I'd had the IO thing on 2 slides, and I pulled this up at the last minute. I mean, let me just paste it in another piece of code. Let me just totally screw this up. We'll try the operator. We'll make operator. Oof. What's going on? Must be a binary operator. I'm gonna regret this. Let's get rid of all this down here. Shouldn't really need any of that. Nope. Yep. Good spot. I have no idea how I tried to explain it with the bad code before. So we got here, yeah, operator must be a binary. I mean, this one here is just getting confused because it's like it doesn't understand it, right? When I scope it, it can make sense of it. So yes, anything that's a member function needs to be scoped to the class. Anything that's a friend doesn't.
And then we had overloads before that. You said you wanted to do that?
Yes. Which is defined here, but it's basically just the pluses, minuses, it's the less than equalities, and it's the output stream. Generally, if you're feeling a bit uneasy about it, I think it's important to remember most operators in C++, most work on 2 things. Add, subtract, output, equality. And every single one of them works on 2 things. It's just a question of, are both of those 2 things passed in as parameters, or is one of them the object itself? And you can actually derive whether it's a friend or a member function relatively quickly with that, because if you think about it, it's like when I times equal something, when I times equal 0.1 to 0.2, there's kind of a reference point. Like I am 0.1 and I am timesing equal it to 0.2. Whereas when you look at adding 2 points together, there's no real logical point that you're operating on there. They're just kind of 2 random points in the ether producing a new point. It's the same with output stream. And then other ones make sense as well because it's subscript and plus plus, that is the point you're working on. So in my head, I'm always I always just try and remind myself these things are always member functions, but there are times where it just wouldn't make sense, like the addition, for them to be member functions. I don't think we cover it in the slides here too much either, but if I just continue this butchering bit I've got here, and I'll try and, I'm thinking, what's the operator plus overload again? It's point operator plus point const reference P1, point const reference P2, and then I was doing, you return a new point that was P1 dot x plus P2 dot x, right? Now, and then you have to go mark this as a friend. So that's you going along and then making this one here. But important to note too, I do see people sometimes also just go and say, well, point, or say like auto p equals point p1 if like copy constructor exists, and then they just say like p plus equals p2 and then just return p. You know, so a question when it comes to doing all these operators is that idea of like, how can I define the core logic the least? What I mean by that's like when you're defining less than, greater than, less or equal to, greater than equal to, one of those functions should probably be the base definition of what relational comparison means, and the others will just reuse that core logic. And I'm doing the same thing here with the plus operator, because now the plus operator doesn't actually even need to understand how adding 2 points works together, because it's kind of delegated that understanding to this one. So if the definition was to ever change of how 2 points were added together, it only happens in one location. And that's, you know, a good thing in general with programming. Yeah, Sulux has also asked, when it comes to returning it, why is it this? Makes sense. I kind of get this. This is a pointer to the object itself. It's true in most languages. I think, yeah, I think it's true in most languages. So we kind of have three options here. We can either return a pointer to point, in which case this would work, right? Or we can return a point itself, in which case this would work, because you can't, you know, if you're going to return a thing, you need to return the thing, not a pointer to it. But this would result in an unnecessary copy. Or you can return reference, though I don't actually know if the reference there would... Oh no, you kind of need to do that. Yeah, because if you didn't have the reference there, it might even still compile. Let's try it out. I have to change that. Yeah, so this is a good example. You could do this. Like the compiler isn't super finicky with a lot of this, because it's really not demanding that you have to follow everything a certain way, which is kind of where you can get tripped up on this, I think, unless I'm compiling the wrong one. But this would just be a bit weird, because it means like if you have 0.1 and then you plus equal 0.2 to it, it's going to give you a whole new point, right? Without it being a reference. You're also quiet. Such a lovely group to talk to. Don't have too much left. We're not going to run till 8 tonight, so I'll just kind of keep going. Was there another question? Okay, sorry. We can operator overload the assignment, operator equals. The assignment is where someone comes along and says, like, you know, what's a good example? It's if someone says, you know, auto p equals 0.12, and then someone says, like, auto q equals p, like that. You know? So q is a new type that, maybe not even that. Because it gets really tricky, because that's technically copy construction there. So like last week, well, in the week 3 lecture, we talked about classes and how you can define a constructor for a class, and then you can define copy constructors and things like that. I don't think we really define copy constructors too much, but well, most copy constructors are synthesized. And what I mean by that, if I'm just taking a quick tangent back to copy constructors, this point here is a constructor. I could make a copy constructor that takes in a reference to a const point called p, right? And then I could, if I wanted to, just really loosely say that, well, this dot x equals p dot x, and I could do the same thing for y as well. And now I've created a copy constructor. I've told the compiler how to deal with a second type being copied here. But I don't actually need to do this, because the compiler by default will synthesize a copy constructor for me that will just copy all the same data fields across. So and that's why often we don't have to define a copy constructor, because if you're just doing this, you don't need to. The compiler will just figure it out. And what we were saying in that week 3 lecture was that sometimes you actually don't want people to be able to copy construct your stuff, in which case you need to explicitly say, don't create that for me. I don't want it to be possible. But my point is, where things get really weird is because Q is not a anything yet. It's not already a point. It's like to be a new thing. This, whilst it looks like an assignment, will actually copy construct, which makes sense because Q's not a thing yet. The equivalent of what I maybe was talking about was if you had 2 points here, and what you actually then wanted to do was or maybe 3 points. I'll call them A, B, C. And what you actually did then was you said, actually, I want A to be C. That's an assignment operator. An assignment operator is where the left-hand side has generally already been created. It's already a thing. It exists in memory. It's right there. But you're now kind of just reassigning stuff to it of the same type, which is, again, very different from auto Q equals C, because that's a copy construction, and that's we call that a copy assignment in that case. Funny little thing. But obviously, another copy construction that could look even more like explicit might be like if someone did this. So these two lines here are the same, just because the compiler will infer it. Someone says, what happens if you do A equals A? I don't know. I don't think we have the code right here to try that. Either the compiler would just be like, sure, let's do it, or it'll just be like, you can't do that. I'd guess on the latter. Because like it would be like, you can think about it from the perspective, if you're a compiler writer, why would you not stop that? There's never a case where you'd want to say equals A. It's completely deterministically detectable when you're scanning through source code. So just throw an error. That would be my guess. But I'm not sure. You could try it out. Anyway, assignment operator, again, quite straightforward with these points because someone gives you a second point. You're a current point. It's clearly also not a friend because when you assign something, there's like a subject to it, right? Like I'm the subject of it. And you'll also see that this one returns a point reference. And I think that's important because this also starts to make you think about how some of this code works, because if we look at assignment here, and I create like an int main, and we create a point. When it comes to assignment, if you were to, I don't know why I just rewrote this twice, sorry guys, C, and then I say C equals P. You can kind of do this if you want to, I think, right? Because and then you can start to infer how the language works, because if you think about C equals P, you are now trying to copy assign P to C, but what is the return of that particular operator? It is a reference to the point itself, the point that's being updated, which in this case is C. So what happens after that operator completes is this returns as C, and then I print it out. So this line here would, in theory, do the assignment and then do the standard out. Now you might not even, C++ operator, you might not even need to do that because you just go back to your friendly operator precedents online and you have a look at where the assignment is. Direct assignment's there. I'm just assuming that the output stream is like the absolute lowest. So like even if you didn't have those braces, it would still probably work. Oh, it just hurts looking at that, doesn't it? It's a horrible line of code. You're doing cool for temperatures? The aircon turned off like half an hour ago, but I left it off because it's probably cold. Yeah, I'll turn it back on then? Yeah? No, you don't care, do you? Okay, how many more we got? Subscript, increment, arrow, type conversion, 4 more. Someone says, what's meant by compound assignment on the slide? Oh, it's similar to compound assignment in that like it's a member function. It's fairly straightforward. It's not adding anything. It's just kind of saying, they're both member functions and stuff like that. All right, subscript. Subscript, little brackets. There are a bunch of operators like, someone asked something on the Slido. They said, is overloading the same as overriding? I mean, yes, in like conceptually. I don't know if there's a technical word for operator overriding or something like that. But yeah, no, I mean, it's overloading just means to, like overloading is like there might be a definition for it and you're going and loading a new definition on top of it. But if you're just talking about it with a friend, yeah, like operator overriding, it makes sense. Someone says, in most initialization cases in C++20, like auto p equals point, they're talking about this line here, is where mandatory copy Elysian applied. I mean, no copy constructor is called. I don't quite understand that. I might come back to that question at the end if that's all right. All right, so we have subscript. Most types you define are not going to have subscript, but some do. Standard string does. Remember, subscript is, actually, let me just, let me go back to a basic piece of code. I want to start running some of these pieces of code again with you. I'm just going to hijack the overload assignment one. Why? Whatever. Yep. So let me just copy this in now. So what I've got here, and it's really silly if you think about it for too long, I have gone and put an, I have to hash include assert too. I'm just going to get rid of the asserts. They're not really that necessary. Right, so what this subscript one allows me to do here is to basically do the equivalent of printing out A0, A1, like that. Right, now, in this case, this is a terrible, I mean, maybe it's not terrible. I don't think this is a great example of where you'd use subscript. But we've just decided to say, well, if someone tries to subscript 0 for our point, we'll give them the x coordinate. If they try and subscript y, we'll give them the, sorry, subscript 1, we'll give them the y coordinate. So we've gone and created two functions here. Just worry about one at the moment, pick any we want. It makes sense. If someone passes in I as the subscript, we return them x, otherwise we return them y. Okay, so we've overloaded subscript, which is why this particular thing here works. Now, a couple of things to note with subscript. Well, the main thing to note is that this is where we start getting into some of the operators that get multiple definitions, which ties into what we talked about last week with classes and const correctness. Because if you remember with classes, towards the end we talked about const correct classes where we said, hey, all of your functions, all of your member functions in your class should be const where they can be, and if they can't be, they should be not const, and if they have to be both, you make them both. And this is actually an example of where we need them to be both. So what I mean by that is that here, this is our non-const subscript operator. This is saying this is what happens if I have a non-const point, because you know what can happen with non-const points? Someone can come along and do this. They can set A to be 4. They can modify it, right? Because they can access it. However, we also need a const version of this, but a const version of this doesn't need to really return a reference because it's not modifying it, and it can't modify it. So what the const reference is used for is if someone came along and had a const point, they can't do, they can't do this here, in this case, right? But you know what they can do? They can still actually print it out. What I mean by that is you don't need the non-const version to, like you only need the const version to, the const version allows you to print stuff and access stuff. That's what we're doing here. We have the const version for that. If we wanted to modify it, we need a non-const version as well. And that non-const version would then allow us to do this. I do need to make sure that my point is not const, naturally, because if my point is const, it's always going to go straight to the const function, right? So if the point's const, it goes straight to this const one, and then where the compiler gets really confused, and we talk about this later in the course, but when this function returns an int, a compiler doesn't understand how to assign a value to an int, right? Because like this const operator returns like 1. That's what this does here. So it returns 1. And then what you basically end up with is asking the compiler, hey, 1 equals 4. And the compiler's like, absolutely not. I'm not going anywhere near that insanity. Whereas if we mark it not const, the compiler will look for the not const version before the const one, right? So a non-const object, it's happy to fall back to a const one. So if I don't have this and I wasn't trying to do that, this works fine because a non-const object can call a const object member function, const class member function, but a const object cannot call a non-const member function. Teaching this course is just tongue twisters, really. However, this works with the reference because the way references work in C++, references still mean something. So in this case here, it's not the equivalent of me saying 1 equals 4. It's kind of the me saying, hey, a reference to that x coordinate of the point thing equals 4. That's what that line's trying to say there. And that's okay because this is now a reference. So this is an interesting case of operator overloading where we do a const and a non-const version of it. So interesting, isn't it? Very finicky. I feel really dumb when I started this lecture. I was like, this is my favorite lecture. And a bunch of you right now are like, what is wrong with him? I just don't think it's kind of boring, I won't lie. But it's not too hard, you know? If you actually look at the code we've written, all we've really done is like write x plus equals x and y plus equals y like 6 different ways. Cool. Don't worry about the asserts. All right, increment, decrement. This one's a different class because increment, decrement, I wasn't too happy with the point example. But now we've got a class called road position. And this road position takes in an integer, which is kilometers from Sydney. That's how we're measuring our road position. We have an operator plus plus that just increments the road position. We have a function called tick. I can't remember what tick does off the top of my head. And then we have a function called kilometers, which gets us the number of kilometers from Sydney because kilometers from Sydney is a private field. This was inspired by some random code from some years ago, but it kind of makes, yeah, okay. And where this code kind of came from was like, we had this piece of code that was measuring how far you were from a city, like Sydney, and you would do something, and every time you'd kind of make a step, you'd do what's called ticking, right? Which is like you're just kind of moving another step, like another kilometer away, like a clock ticking. And what we've done here is we've decided we have this function called tick, which you can call if you'd like to. Maybe we'll just make it private for simplicity. And the operator plus plus, what it does is it's just going to call tick for us. That's just an abstraction. It doesn't really need to be there. And all that's really going to do is increase the distance from Sydney by 1, right? So every time you do operator plus plus like this, so you set the road position as 5, you print out the road position, and then you do like road position plus plus, and then the road position is going to be further down the road. Not too hard. But the funny thing with increment and decrement is that we actually need 2 different operators for post and pre-increment. I think the way that the language decides to separate these out is pretty weird. I understand why they can't do plus plus operator and operator plus plus, because whoever defined all these operator overloads was like, they must start with the word operator and then some stuff after it. They can't start with plus plus. So the weirdo way that they decided to do this was to put like, oh, it sounds really mean. I find it weird. Maybe I'm stupid. But they put an int as a parameter. So this one here is a pre-increment, and this one here is a post-increment. Now the interesting thing about the pre-increment and post-increment, because this here is a post-increment and this here is a pre-increment. Pre-increment just means the plus plus is on the left, post-increment means it's on the right, is that with a pre-increment, you literally just increase it by 1 and then return itself. You know, so if I'm a type, plus plus type, increment by 1 and then I return myself. Whereas with a post-increment, what you have to do is you have to take a copy of yourself. Like, you don't have to take a whole copy of yourself. Actually, you do. Sorry. you have to take a whole copy of yourself. So that's just a copy construction there. And then you increment the old version of you, and then you return the new version, if that makes sense. So it's like I'm like a distance from Sydney. Let's say I'm 5. Someone says like road position plus plus. What I do is I take a copy of myself, I put it here, and I move 1 further down, so I'm 6. And this copy I made is back here at 5, and then I return 5. So you kind of clone yourself and return that whilst you still move ahead after. Now, the reason you probably haven't noticed the difference of this is because through most of your computer science things so far, you have probably done nothing with the result of the calling of an operator plus plus, or plus plus operator or operator plus plus. But in this case, we're going to do that here is instead of just benignly calling that, we are going to say road position plus plus dot kilometers and then plus plus road position kilometers. And I'll go make operator overload increase decrease and run it. And I get 557. Now this is really interesting because I'm at 5 here. When this line is called, I'm now at 6, but it printed out 5 because what it was printing out the kilometers of was the copied, the cloned version before it was incremented, post-increment, right? So we like return it, we increment it after we've returned it. That's why they call it post-increment. But then the pre-increment, we increment before we return it, which is why it's 7. So if I was to swap these around, for instance, you would see this go from 557 to 567. And similarly, if I was to make it go this way, you would see that go from 567 to 556. This is also where we start getting into the idea that plus plus is finitely quicker in some cases because you're not making a copy. Imagine you have a very big data type, right? Data type might be like 200 kilobytes, and then you're looping over this data type, incrementing it a whole bunch of times. Now in reality that's often not a concern, and then what happens is people kind of go out there and they start saying, oh my god, like 4 into I equals 0, I less than a billion, plus plus I, and they're like, ha, I'm saving like many things of time and memory. But the compiler is actually quite smart because you'll often hear about a better way to program, but the compiler will figure stuff out pretty quick. If the compiler, for instance, and I'm 90% sure of this, by the way, most things I tell you, just assume that like 2% of it is wrong or outdated. I don't know which that is. People figure that out eventually. But here, if you were to do, say, I++, I'm pretty sure the compiler's smart enough to identify that, realize you're doing absolutely nothing with the return type, So if you're not doing anything with the return type of a post-increment, there's no value to it. So you might as well just do a pre-increment. So the compiler's like, well, if you're not going to do anything with the thing that you're asking someone to copy and give you, we'll just call the simpler one that saves memory. That's an example of where compilers will optimize sometimes, and why we can learn these interesting things about code. And const code is sometimes faster too, because you don't need to worry about it being modified. But then again, the compiler will sometimes see if you've written code that should be marked as const that isn't, and it might mark it as const if it can get a speed bump from that too. All kind of crazy magic that goes on that most people wouldn't really know a huge amount about. Yeah, so that's pre-increment, decrement. I don't really have a lot to say on arrows and dereferencing. This is using some kind of malloc and free in C++ are new and delete here and here. I might not spend much time on this example, particularly because I don't even know if it's in the assignment 2 spec. I can't remember off the top of my head. There's a lot of different things in assignment 2. But I don't think so. Let me check. That wasn't going to be very helpful. Yeah, it's not. So I don't think there's any big need to spend time on it. We could always loop back to this example in week 5 when we talk about resource management a bit more. Here, at the end of week 5. So let's not worry about that. And then type conversion, which is the last one. You can also define an operator that will basically do the static casting for you. Now the example we've got here is a fun little one, which is essentially talking about how if someone gives you if someone tries to cast the point you've made to a vector. Because you got to remember, when you do a static cast from like an int to a double or a double to a char or anything like that, anytime something like that happens, someone, whether it's the writers of the C++ compiler or whether it's the writers of an STL library, someone needs to define that, you know? Again, the compiler can't just static cast anything to anything. You can pretty much static cast nothing to nothing until people program it in. And again, obviously ints to doubles and doubles to ints and things like that. Someone just went and did that really early. But if we wanted to turn our point to a vector, that's a bit harder. The way you do that is you say operator and then you follow it with a type like this. And now I'm saying, yep, this is the operator to turn things into an int. And when someone calls that, I create a new vector. I push 2 elements to it. And then I return that vector. And how the compiler knows if to invoke that is to, when you take your p, your point, and you try and static cast it to a particular type, the first thing the compiler is going to do is go to your type point and look for any operator that is the type conversion to that type. And if it sees that, it'll do that. So this code will now work if we go and run it. That'll work fine. But if I was to say, I actually want to turn that into an array, the compiler is going to be like, well, actually, it's complaining here because it like needs a specific size. But if we get past that, it's, here you go, no matching conversion for static cast from point to standard array int2. It's actually really specific what it's upset about, which is you haven't gone and defined it. And you know what? We could go and define it if we really wanted to. This, I don't know. Do you need to have a number there? I'm making this up as I go, so this might be a little bit. Hope this works. Array. Not quite. Oh, we don't need the p because we're in the class. All right, so there you go. Now we made ourselves a little array. Works fine too. So that's how we do some static casting stuff. I don't know where that's used specifically. I'm not familiar with every single STL library, but you go and try and static cast a standard string to a char array or something like that. There's probably some kind of castings that people have baked into that. Last thing is when we look at operator pairings, many operators should be grouped together. This table basically tells you that if you go and define a certain thing, then you should go and define the other thing. Now, what isn't immediately clear here is that I don't want to get you confused into thinking this is operator plus for like a point and another point. This is actually something kind of a little beyond what we're doing, which is like if you say define an operator between a point and another point. Maybe you've got 2 point classes out there, like a complex point and a Cartesian point, or 2 different types that you might want to add together. I think another good example is I did this lecture this morning, right? And in JavaScript, you can add a point, you can add a number and a string together, right? In JavaScript, it converts the number to a string and then it concatenates them together. So you can add string to number. All this table is really saying here is if you define how to add a string and a number, you should also define how to add a number and a string. Because the compiler will not just randomly swap all the things around. So, just to give a JavaScript example, which is a bit trite, it was I think it was a console log of hello plus 5. The point is, imagine those 2 things are complicated types. You need to imagine that someone is also going to pass in 5 plus hello as well, if there are different types being passed in. Because if you have some definition somewhere, not that this makes much sense, where you had a standard string and then an int, if someone was to give you these in a different order, then it's not going to just figure that out. It's not just going to swap the pluses around and be yeah, I'll just swap them around. You actually need to go and define this. the other way too. So that's what those ones are with the different types. You'll also see if you define pre-increment, you should define post-increment. If you define minus minus in general, you should also define plus plus. A few other things. And I mean, I think like you could really expand this table if you'd like to. Like even in the chat, Tim's talking about if you define plus equals, then you should also define plus. I don't know. I don't want to disagree with you, but I could imagine if someone was like, yeah, there might be a point that you never want to allow someone to create a new point by adding two together, but you want to allow them to like, you know, extend a point, you know. I don't know. I've been honest since the start. I don't have enough, years of industry C++ experience to give you lots of anecdotes about random edge cases. So I'm not sure, but yeah, I mean, there's probably some others not in this table that you could reference. Someone said how to define plus TU. I kind of just did a really tripe example of it here, where I was just like, you would just define it with two different types. Again, the point thing that we've been using is so simple that it's not strictly obvious where you'd have a case like that. But a case where this might make sense, which we kind of get to later in the course, is, when you deal with inheritance or something, like imagine you have, you have like a list type and there's two subtypes of it, which is like, one type of list, like list A and list B, and they're both, inheritance classes and things. So there might be instances where you need to like be able to add two very closely related but still different types together. Things like that would be where you'd be dealing with like that U and that T being different. Did you have a question?
Yeah, what if, so for that example, like int has its own operator overload for plus and string has a different overload for operator plus? What different things?
Well, this is kind of, and this is actually, so the question was like, if both string and int know how to add, which one takes precedent when you add them together? This is kind of why the, it starts to make sense why some overloads are friends and not members, because yeah, if they were members, there'd be that kind of idea of like, which object do I look for? But in C++, if you just literally have like a main function and all you do is just say, hey, I'm going to try and add Hayden to 5. C++ doesn't really look in a particular whatever. It will just go hunting in all of the the code, the compiled code, for anything that has the pattern of, this. And if it finds something like that, it'll do it. Maybe in that case, it might actually be looking initially for like a char star s potentially, because it's not technically a string in that case. It's like a, string literal. But just to really clear that out, it's probably more like, if it was this, because then it would look specifically for that that line there. But the point is sometimes to do those additions, because we need access to both the string and the, not the int, but the equivalent, that's when we would go and take our operator that we've defined globally, and we would add like a declaration line in both classes as friends if we wanted to access both types members, things inside them. This stuff isn't as, for anyone who's finding this kind of weird, this isn't as hard as it seems either. Probably like a third of the random stuff we've talked about like this is very academic and theoretical, which I know from talking about this so much. But yeah, I wouldn't really stress about it too much otherwise. It is a big part of assignment 2. So assignment 2 really quick. It's due end of week 7. Honestly, it's like the longest the longest time any students in any courses I teach have an assignment. It's like 4 weeks. It's not that hard either. In terms of hours till due to difficulty ratio, this is like top notch. Assignment 3 is a little harder though, so get ready for that. Ideally, I'd make this one due earlier and assignment 3 have 4 weeks, but the uni doesn't let us make anything due in flex week. And I was like, I could make it due the Monday of week 7, but like, why? It's like, you're all adults. It's not like it's going to push back any dates. So it's due at Friday of week 7. The content you need for it is largely, or nearly and totally, I'm pretty sure, I'm pretty sure, I'll just double check, but it's mostly today, week 3 classes, and also custom iterators. So for most of you, you might find parts of assignment 2 right now a little bit hard to like start. I think most of you could start it after this today. It's not crazy hard. But what we do on Wednesday should cover like the last 10-20% of it, and then we will actually talk, because that custom iterators thing's pretty short lecture. We will actually just spend a lot of Wednesday talking about assignment 2 together. So that's what we'll be doing. Yeah, assignment 3 will be released earlier. Yeah, just to be clear, we're just finishing up a few things on that, but we will release it definitely earlier, probably in like end of week 5 or something, if people really want to look at it. Assignment 3 does rely on all the content till the end of week 7 though anyway. Any other questions today before we wrap up? Yep. Oh, me, I start with fruit and then I run out of fruit. Like I'm like, think of random fruit, and then I was like, I'm out of fruit, then I went to food, and then I ran out of food I could think of, and then it just ended up being random stuff. So just add some color to the page. Have a good night. Go home, don't be too cold. It's a cold night. It's going to get to 4 degrees in 2 days, so watch out.